Hello again, students. In this video, we are going to solve the exercise question number 30. This question deals with the electric field due to a long straight charged wire, right? We have found the electric field due to such wire by using the Gauss law. We get the answer E is equal to lambda divided by 2 pi epsilon 0 r. But for this question, as you can read from the book, we have to do it without using the Gauss law. So that means we must do it using integration only. So let's start. So first of all, here is that long straight wire. Here is that point P, which is at some distance r from that wire, right? So to find the electric field due to the entire wire at this point, what we have to do is we will divide the whole wire into small portions. I have shown two such small portions which are located symmetrically around this point C. Okay, so that means the electric field due to this small portion is in this direction, dE vector, and the electric field due to this one is in that direction, that's dE. So ultimately, the net electric field at this point P is going to be on the right hand side. Okay, clear? In the radial direction. Okay, so that electric field must be, if I define this angle as theta, then that electric field must be 2 dE cos theta. I don't think you have any problem because vertical components are cancelled and the horizontal ones remain. So now, what we are going to do is we'll find the electric field due to the entire wire by doing an integration of this thing. Right? So let's see what we have. So we are considering two infinitesimal portions or elements of this entire wire, right? Each having length dl, and that's why each will have a charge dq, right? So charge on each element that I have shown here, charge on each element is dq, which is going to be equal to lambda dl, and that's because lambda is defined to be the charge divided by the length, right? So because this has a length dl, the charge is dq equal to lambda dl. Now we are going to find out what is the value of 2 dE cos theta, right? So electric field at P due to these elements, right? So only due to these elements, we'll do the integration later, is 2 dE sin theta, 2 dE cos theta. I hope that is absolutely clear, right? And that is equal to 2 dE is the electric field due to one element, right? So this is going to behave just like a point charge, and if I want to find the electric field due to a point charge, it is k q, that is the charge, that is dq here, right? K dq by distance square. So I want to find out this distance, right? So I'm sure you do realize that the distance is going to be under root L square plus R square. So ultimately, I can write the hypotenuse square is L square plus R square. Excuse me. Now into cos theta, right? So we still have to write cos theta. So look at this triangle, either one, right? And clearly cos theta is equal to R divided by under root L square plus R square, right? Again, L is taken to be the distance between C and that element, right? So this is what we have got for 2 dE cos theta. There's one more thing we can do. We can put dq's value. So if I put dq's value here, I'm going to get lambda dl. All right, right? To simplify it, 2k lambda r dl divided by L square plus R square raised to 3 by 2, right? So this is the electric field only due to these two elements, right? Now if we will integrate this, we will get the electric field due to the entire wire, right? So let me erase what I've written over here. So I could write electric field due to the whole wire is E, obviously is the integration of 2 dE cos theta. I hope you realize why we have to do integration of 2 dE cos theta, right? Because this is the net field at this point due to both of these, right? So if we do an integration of 2 dE cos theta, right, from L value being, well, the smallest value of L is going to be 0 and the largest value of L is going to be infinite, alright? So I can write this to be 0 to infinite to k lambda r dl divided by L square plus r square raised to 3 by 2. Okay, so that is what I have to do an integration of, right? So let's do that. So this E is going to be equal to, well, 2 is constant, k, lambda, r, they are all constants, right? So we are only left with doing the integration of 0 to infinity dl upon L square plus r square raised to 3 by 2, right? Okay. So how much is this going to be? Well, to do this integration, there's no direct formula, right? So you'll have to use a maths technique called substitution, right? It is okay if the biology students will skip all that portion, no problem with it. If you want to learn, definitely have a look. It's not very tough, right? But it's a bit different. We haven't been doing such things often in physics. So let's start. To do that, I'm going to use this diagram, right? I'm sure you realize that if I will take tan theta, I'll get tan theta is equal to L by R, alright? Okay, so that is what I'm going to use. So I can say L is equal to R tan theta. And when I do differentiation of this with respect to theta, so dl by d theta is equal to R, and differentiation of tan theta is sec square theta, right? So I'll get this quantity. So ultimately I can put that dl is equal to R sec square theta d theta, right? Okay, so if I use it here, I'll have to also convert the limits. So that is if theta is equal to, if L is equal to 0, if L is 0, put 0 here, you get theta equal to 0, right? And if I put L is infinite, that is tan theta is infinite, that's only possible if theta is equal to pi by 2 or 90 degrees. Okay, so using all this information, if I put it here, so I'll get by substitution of all this information, I get electric field at P is equal to 2k lambda r integration of, where L is 0, I have to put theta is 0, that is 0. Where L is infinite, I have to put theta is pi by 2, that is the upper limit. So 0 to pi by 2. Instead of dl, I will write r sec square theta d theta as is given here, divided by L square. Instead of L square, I am going to write r tan theta. So this bracket is going to be r square tan square theta plus r square, the whole raised to 3 by 2. Okay, now the next step, 2k lambda, r into r is r square, right? I can't do anything with the sec square theta for the moment, I leave it like that, divided by, over here r square is common, and when I'll take it out, it's going to be r cube because of the power 3 by 2. Not only that, once I take r square common, I'll have tan square theta plus 1, and I'm sure you know tan square theta plus 1 is sec square theta. So sec square theta and raised to 3 by 2 from 0 to pi by 2. Alright, so I'll get 2k lambda r square integration 0 to pi by 2 of sec square theta d theta upon r cube sec square theta raised to 3 by 2. Right? So now I'm going to put the next step in here. So that is going to be E is equal to 2k lambda r squared upon r cube. Again, because r is a constant, you don't need to keep it inside the integration. Integration of 0 to pi by 2 sec square theta d theta divided by sec cube theta, right, divided by sec cube theta. So ultimately, I am sure you realize this will become integration of cos theta d theta, because sec square theta upon sec cube theta will be cos theta. Integration of cos theta from 0 to pi by 2, so that is going to be 2k lambda upon r. Integration cos theta is sin theta, right? So sin theta from 0 to pi by 2. Alright. So I'll get 2k lambda r and put value. So 1 minus 0 is 1. So that's it. We've got the electric field at this point is 2k lambda by r. Right? Again, k's value is 1 by 4 pi epsilon 0, if you want to put it that way. So 2 cancels with 4 and you get lambda is equal to E is equal to lambda by 2 pi epsilon 0 r. Right? Obviously the same value as we got using the Gauss law, right? So this is the whole process, right? So if you want to skip over the integration part, it's fine really. Okay, all you could understand is that finally when we do an integration, we are getting sin theta, right? And we put sin theta's value as sin pi by 2 minus sin 0, so we get this answer, right? So that's it for this interesting problem.